In this video, we are going to discuss questions 7 to question 10 of question paper 419701 chemistry, that is A-levels chemistry of the examination series May-June 2025. Question 1 to 3 and question 4 to 6 are already discussed in our earlier videos, two different videos, and in this third video, we are going to discuss question 7 to question 10. So let's start with question 7. It says a hydrocarbon is known to be either compound D or compound E, and the D and E are already given here. The structures are given. Question A, sub question A is give the systematic name of E. Now E is here. Let's see what is there. There is a benzene ring here at the, and then there are 1 and 2 ethyl groups bonded to benzene. So how are we going to name it? If we number this carbon as 1, then 1, 2 and third position of carbon, again there is an ethyl group. Or if we number this 1, 2 and 3, it's still going to be the same. On the third position, third carbon, we have an ethyl group. So how are we going to name it? Is that 1,3 diethyl benzene, 1,3 diethyl benzene. So this is how we are going to name it, the systematic name of E, where E is the benzene compound. Now here the proton NMR spectra of D and E are compared. They are very similar. The proton NMR spectrum of D is shown in figure 7.2 here. So let's see what's next. Suggest a suitable solvent for obtaining the spectrum in figure 7.2. Now the most common solvent is CdCl3, where D is the deuterium hydrogen, that is simple hydrogen is replaced by the heavy hydrogen deuterium. So that is CdCl3 is a very common solvent used for NMR spectroscopy of proton. The proton NMR spectrum of E is obtained twice, once before and once after shaking with D2O. Describe any difference between these two spectra. Explain your answer. Now let's have a look at structure E. Here is the structure E, and we can see that there is a simple benzene ring bonded to 2 ethyl group. Now with heavy water, it can change only when we have an OH, that is alcohol group, or NH or NH2, that is amine group in our compound. But here we don't have any such group, so here we'll just write that no difference in proton NMR before and after shaking with D2O, as there is no OH or NH2 group, because it will change only when one of it is present in our compound. Now the third question is complete table 7.1 for proton NMR spectrum of D. Now let's understand what is a D proton NMR spectrum. Here it is 1.3 chemical shift at 1.3 ppm, 2.7 and 7.1. So let's see these three peaks, 1.3, 2.7. So here it is 1.3. We can see that's a triplet. Correct? At 0, this is for the solvent, or you can say that is the reference peak. At 2.7 we can see there is a quartet, and at 7.1 there is a singlet. So remember, it's triplet, quartet and singlet. And let's see this, compare the chemical shift. 1.3 comes in this range here. Let's look at table 7.2. 1.3 comes in the range of this alkane group or alkyl group bonded to something else. Now here we can see that it's a triplet. At 1.7 is a triplet. That shows that besides this carbon there should be a CH2 group, because triplet means the adjacent carbon have 2 proton, so we get a splitting of 2 + 1. That's how we get. So besides have a triplet CH2 group, which gives us triplet. So let's understand now. Look at the structure of D and understand how come we got the triplet for D. Now in this D compound, if we have two ethyl groups and we are getting a triplet, that should be for the CH3 group, where besides it is CH2 group, right? So the splitting is triplet. So here we can write that yes, here the proton NMR spectrum of D is given. We can see it's a triplet at 1.7. So we can find out, and so the total number of hydrogen responsible for that is 6, because there were two ethyl groups. So group responsible for the peak is a CH3 group, and the splitting pattern is triplet. That's what we have written. Now 2.7 we can say it was quartet, and 2.7, yes, here we can see that it comes in this range. So it's any ethyl, methyl or alkyl group bonded to AR. AR is an aromatic ring, that is benzene ring. So we know that it is for the CH2 group which was bonded to benzene. This CH2 group is going to give the peak at 2.7 because that's directly bonded with the benzene ring. And yes, it has CH3, that is 3 protons on the adjacent carbon, that is 3 plus 1. It's a quartet. So this is how we get quartet. So CH2 group responsible for the peak, and number of proton are 4 because we have two such CH2 group bonded to benzene. So here we can make out this again 7.1 shift. 7.1. now here we can see it's almost in this range, 4.7 to this again, then it comes in this range also. Yes, so this is because of the proton of the aromatic ring, that is benzene ring, because in our we don't have phenol, right? So it is only for the aromatic proton. So we know that here it is for aromatic ring. Now its group responsible is benzene. We know that splitting pattern is singlet, we don't have to write. So how many protons are responsible for this? Now let's understand here the two groups. The two carbon are occupied by ethyl group, so there is no hydrogen present on these two carbons. So how many hydrogen left on the benzene ring? 1, 2, 3 and 4. So there are 4 proton responsible for this peak. So let's see what's next. Here after this is, yes, the fourth sub question, compound D and compound E can be distinguished by carbon 13 NMR spectroscopy. State the number of peaks in each spectrum and carbon 13 NMR of D and carbon 13 NMR of E. So D and E, let's analyze the structure and find out how many peaks are possible for carbon 13 NMR. So now here is the structure of D. Let's understand. What I suggest my students always is first draw a line of symmetry if it's there in our compound. So here we can find out there is a line of symmetry here. So besides this line of symmetry, so on two sides of this line of symmetry, if there are carbons in the similar environment, they're going to produce the same peak. So let's find out how many peaks each carbon will produce. So starting with the ethyl group which are here, we can see that the 2CH2 group is going to produce one peak. The two CH3 groups are going to peak the second type of peak. The third carbon, the third peak will be produced by this two carbon. The fourth peak is going to produce by these two carbon because it's on the opposite side of the line of symmetry, and the fifth peak will be produced by these two carbons. So here for D we should get 5 peaks in the carbon 13 NMR. And let's see here in D, if we draw a line of symmetry, we have it here. Yes, again the 2CH2 group are going to produce the first kind of peak. The 2CH3 group is going to produce the second type of peak. The third peak will be by these two carbon. Sorry, the third peak won't be by this. The third peak is here. The third peak will be by these two carbon. The fourth peak will be produced by these two carbons. So here is fourth. Now here these two carbon are not same. Why? Because here the fifth peak is produced by this carbon, because besides this carbon the other carbon carries the ethyl group. So this is another kind of, and this is the sixth carbon which is going to produce a sixth peak, because that is much farther from these ethyl groups of the benzene. So D is going to produce 5 peaks and the E is going to produce the 6 peaks in our C13 NMR spectrum. So here we go with the next question. C. The compound D can be oxidized to compound F by alkaline KMnO4 followed by dilute acid. Now D is oxidized to F. Here is the structure of F. Write an equation for this reaction using molecular formulae of D and F, and the products of this reaction are F, water and carbon dioxide. Now use O to represent one atom of oxygen for the oxidizing agent. Now let's understand what's the molecular formula of D. If we count the carbon, then we have C, 10 carbon in D. Then we have H14. If you count the 4 carbons, yes, 4 carbons on the benzene ring and the remaining 5 carbon each of the ethyl group. So 10 plus 4, 14. So we have C10, H14 plus the oxidizing agent oxygen, that gives here, if we count the carbon atom, remains not same, because 2 of the methyl group, that is CH3 groups, are gone oxidized as carbon dioxide. So we can say that 2 are less than the D. So we have C8. So let's write C8. Then hydrogen, we can see that we have hydrogen 16. Sorry, 6 hydrogen, 6. Why? Because there are 1, 2, 3, 4 hydrogen and the 5th and 6th hydrogen of the carboxylic acid. So we have C8, H6 and O4. So this is how the structure of F gives us. Then we have CO2, that is carbon dioxide, and we have water also. Now if we balance it, then we need to have 2 carbon dioxide here, because the 2 of the methyl group CH3 group is oxidized to carbon dioxide and 2 carbon are less here. So 2 CO2 is added here, and if we count hydrogen, then we need to add 4 here, because the 8 hydrogen are less in F compared to D. So 4 H2O. Now if we count all the oxygen, then we get to add 12 oxygen atoms here, because total of 12 oxygen is present more in F compared to D. In D we had no oxygen. So this is how you're going to write a balanced equation. Now here we go with the second part, where it is F reacts with an excess of SOCl2 to form compound G. The molecular formula of G is given here, that is C8H4Cl2O2. Now G reacts with ethane 1,2-diol, that is here the structure given, 1,2-diol ethane, to form a mixture of compounds that includes compound J. Molecular formula is given here, and K molecular formula is given here. Now let's understand what is this G, J and K. Understand, G is the one which is formed by reacting F with SOCl2, that is chlorinating agent. Chlorinating agent, then it's going to produce COCl and COCl in place of carboxylic acid, right? So that is the compound or structure of G. So let's draw it properly in the box here. The benzene ring should be given here. Yes, the benzene ring is here. Then the chlorinating agent chlorinates the carboxylic acid to give COCl. So here is the structure of G. Now understand, G is then reacting with 1,2-ethane diol to form a mixture of products which is J and K. both have the different molecular formula, that is C10H8O4. Now understand what is happening. The G is already having 8 carbon atom, and that is changing to C10, that is just 2 more carbon atom are added. So that shows that the 2 carbon atom of the ethane diol are getting bonded to it with no chlorine, but we can see that the 2 oxygen atoms have been added and removed the chlorine atoms, and the hydrogen atom have also increased. So that shows that directly the ethane diol molecule is added by the esterification reaction. I hope my benzene ring is also clear. Now this is the simple G compound now that was bonded to the ethane 1,2 diol, where we can see that the O group, that is alcohol, gets bonded to the carboxylic acid, or you can say acyl chloride, to form an ester. So if you count the carbon, hydrogen and oxygen, this is how it's going to work out. Now K, let's understand K. What is happening here? It's C10H8O4 and here it is C18. Understand, 8 carbon atoms are added compared to C10, H12, Cl2 and O6. Now that clearly shows that we have 2 benzene ring bonded to each other with some hydrogen and chlorine. 2 chlorine atoms are also present. Now what were the structure of G? We know that the G was this with COCl. So obviously if there are 2 benzene ring, we are done with C12, correct? Now we have 2 more carbon atom, so 2 more for that benzene ring, that is 14. That shows that we need 4 more, right? So obviously there is 2 more from ethane diol, ethane 1,2 diol, that 2 carbon atom are present, plus 2 more benzene carbon of the other ring. So if we find out, we need to have 2 benzene ring on the opposite side. So let's draw 2 benzene ring on the opposite sides of each other. Yes, both of the benzene ring are bonded with the CO group. Yes, let's draw that. Now here we need 2 chlorine also and 6 oxygen. Now we are already done with 4 oxygen. Let me draw it the reverse way. Here is C and here is O. Understand that? Okay, let me correct. Now this time I have drawn benzene a little farther, and the reverse of CO I have drawn because the carbon atom is bonded to the benzene ring. Now we need 2 more chlorine and 2 more CH group and 2 more oxygen. So how is that going to happen? We can add chlorine on one of these sides, and these 2 oxygen as usual, CH2 and CH2 can be added. So let me draw it properly. So I'm adding 2 more oxygen here and then CH2 group bonded to each. So this is how we can draw it. Even you can connect the opposite side, that is also fine. So in short, we need 2 chlorine on the acyl groups, that is, and the ester bonds also formed. I hope my structure is clear. Here is COO. Let me draw it again. I think it's required. Now I think the structure is clear. We have 2 acyl groups, 2 ester linkage with the ethane diol bonded in between. Yes, this is how we finish question 7. Let's go ahead with question 8. Here it says bromine reacts with methyl benzene in the dark in presence of suitable catalyst to form HBr and compound L C7H7Br. L is one of the 3 isomers that can form in this reaction. Now A1, the mechanism for the reaction involves methyl benzene reacting with Br plus ion. Now that is an electrophile. This ion is produced when bromine reacts with the catalyst. Obviously, if we are producing Br plus, that is an electrophile, we need a catalyst which can make an electrophile, that is AlCl3 sorry, it has to be AlBr3 because we are dealing with bromine, which produces Br plus, and AlBr4 minus, the overall complex with AlBr4 minus. So this is how it's going to produce the electrophile Br plus. Now, one of the isomers of L forms in much smaller amounts than the other two isomers. Draw the structure of these isomer and explain why it is formed in the smallest amount. Now, we have to draw the structure of the isomer which is found in smallest amount. Now, what we need to understand is that there is a methyl benzene ring. So, here we have CH3, and the bromine can be bonded to any of the carbon given here. Now, if it is AlBr3 with CH3 on the benzene, now if CH3, that is methyl group, is electron donating group, and it's going to direct the incoming electrophile in the second and fourth position only. So what is the isomer that is produced in the smallest amount? Is the isomer produced at the third position of the benzene ring. So third position here, so bromine is produced attached on the third carbon of the methyl benzene, that's going to be produced in the smallest amount. The bromine bonded to second and fourth position will be in the major product. So let's explain this, that the methyl group on benzene, is electron donating, and it directs the electrophile more on second or fourth positions. So the isomer on the third position is produced on a very small amount. Now complete the mechanism in figure 8.1 for the reaction between methyl benzene and the electrophile Br plus, and let's see how is it going to bond. So here we need to draw a curly arrow. Here it says draw all the curly arrows and the charges. Now we know that we are going to make it for the reaction mechanism in figure 8.1 for the reaction between methyl benzene and the Br plus ion. So we should be adding Br either on the second or the fourth position, that any of it we can draw. So if here the Br is given near to the benzene ring, I'll better prefer add it here because this is going to make a big distance Br. So I should draw an arrow otherwise this way. Fine. So I'm drawing it on the second position, but yes, you can draw it on the fourth position of the Br also. Now if I am adding Br here, then it's Br and H both, and CH3 is already bonded to it. Now what am I going to draw is draw a semicircular ring where the carbon carrying the bromine and hydrogen should not have completed ring. So that carbon should not have any ring inside the benzene here with a plus sign in between that ring because it is electron deficient. Now this H bond is going to break and complete the ring by donating its electrons. So let's draw a curly arrow here. So here again we go with the methyl benzene ring with bromine on the second position, and then H plus is donated out. So this is how its mechanism gets completed. Now the B portion, the chlorobutane and the chlorobenzene are added separately to the samples of warm aqueous AgNO3, that is silver nitrate. One of the chloro compounds reacts slowly and the other does not react at all. The first sub-question is identify a chloro compound that reacts and describe any observation. Now what is going to happen is that the chlorobenzene does not react because the lone pair of chlorine is overlapping with the pi bonding system of benzene, and so CCl bond is very strong, cannot be broken easily. But in chlorobutane, the chlorine, that is electronegative atom, can easily react with the silver nitrate to form silver chloride precipitate. So identify the compound. So that is chlorobutane, and it's going to show the white precipitates of the silver chloride. So white precipitate is the observation, white precipitates of silver chloride. Now the second sub question is write two equations to explain any observations in B1. Now in B1, what is observed is white precipitates of silver chloride. Now that is because of the Ag plus and Cl minus reacting together to form AgCl, that is a white precipitate. Now other than that, what is happening here with the chlorobutane part is that reacts with the aqueous AgNO3. Aqueous is, we know that it's already water, so C4H9Cl reacting with water of the aqueous solution of silver nitrate, that's going to form C4H9OH, that is the alcohol is formed and the chlorine is removed or substituted, you can say, to form HCl. So here this is how you're going to write the two equations for the observations. Let's see the third part. Third part says explain the difference in the reactivity of the chlorobutane and chlorobenzene with the warm aqueous AgNO3, that is silver nitrate. And as I already told you that the chlorobenzene does not react with silver nitrate because of the lone pair of chlorine. So let's explain that. The lone pair of chlorine overlaps with the pi bonding system of benzene, making CCl, that is carbon chloro bond, stronger. Now because the bond is stronger, it's not broken and it does not react with the silver nitrate. So the question 9, now question 9 is phenylamine C6H5NH2 and the propylamine, here it's given, can be produced by the different reduction reactions. Now identify an organic compound that can be converted to C6H5NH2 by a reduction reaction. State the reagents and conditions for this reaction. The organic compound which can be converted to amine, that is phenylamine, is C6H5NO2, that is nitrobenzene. It's easily reduced to NH2 with the reagent tin and concentrated HCl. Now for conditions, we have already written concentrated, so I'm writing it again, concentrated HCl. Now along with that, heat and reflux is also needed, heat and reflux. So that's are the conditions required. Now the B part, identify an organic compound that can be converted to propylamine by a reduction reaction. State the reagents for this reaction. What I prefer is C2H5CN, that is a propyl nitrile, but then other than that you can also say it is C2H5CONH2, that is propanamide, can also be reduced in a similar way, and the reducing agent is LiAlH4. That's the best reducing agent which adds hydrogen to this compound and makes propanamide. The third sub question is identify a single test that will distinguish between the phenylamine and propanamide by producing a white precipitate with only one of these amines. One of these amines produce white precipitates, and so it can be distinguished easily with this single test, and that is aqueous bromine or bromine water. So we can write AQ in the bracket here. The amine that gives the precipitate is C6H5NH2 because that easily reacts with bromine at a room temperature to form, let's see what is formed here, the phenylamine NH2 that reacts with the bromine on the 2nd, 4th and 6th position. So here we can name it as 2,4,6 tribromophenylamine. So this is the structure which we are given here. And now B part. Describe the relative basicities of the phenylamine, propanamine and ammonia. Explain your answer. So the least basic is C6H5NH2. In between comes the ammonia and then comes the propanamine, that is CH3, CH2, CH2 and NH2, that is the most basic amine. And the easy description is that availability of the lone pair of nitrogen to bond with H+. Now in this phenylamine we can write that the lone pair of nitrogen in C6H5NH2, that is phenylamine, gets delocalized or overlaps, gets delocalized, you can say even overlaps with the pi bonding of benzene, pi bonds of benzene, that also can be written benzene. So the lone pair of nitrogen is not easily available to bond with H+. But in propanamine, we can say that the propyl group is electron donating, that is the positive inductive effect of the alkyl groups, and so the lone pair of nitrogen is easily available or easily bonds with H+. So easily available to bond with H+, and so it is more basic. So that's how we describe. Let's go ahead with the last question, that is question 10. The propanoic acid, methanoic acid and ethane dioic acid are all weak acids. Draw the display formula of the ethane dioic acid. Now if we know ethane dioic acid, it is C double bond OH. This is the ethane dioic acid, O and H. Draw the displace formula, so we have to draw all the bonds. So this is the ethane dioic acid. Now the B part is the three acids, propanoic acid, methanoic acid and ethane dioic acid can be distinguished using a combination of two chemical tests. Neither testing reagent is an acid base indicator, so we are not supposed to use the indicator for this testing reagent. Now if we want to distinguish with the two tests that can distinguish the three acids, that is propanoic acid, methanoic acid and ethane dioic acid. Now let's understand that the methanoic acid and ethane dioic acid can be easily oxidized to carbon dioxide. So the oxidizing agent is the potassium manganate. So we can write that acidified KMnO4 or manganate ions MnO4 minus, and the reagent 2 is, now out of these two, both of it are going to react with the acidified manganate, but the propanoic acid is not going to react. Now if we both is reacting, how can we distinguish both of this? Let's understand that the Fehling's reagent is going to react with the methanoic acid and not the ethane dioic acid. So the second reagent you can write is the Fehling's reagent. You can even write Tollens reagent. Both of it is going to react and oxidize the methanoic acid. So for propanoic acid, we say no change or no reaction. with the reagent 1, that is acidified KMnO4, the methane dioic acid is going to change it to colorless. So we can write is decolorizes, or you can say it goes colorless. So decolorizes. Yes. With the observation 2, yes, reagent 2 Fehling's reagent, no change here, so there is no change, no reaction. But with methane dioic acid, Fehling's reagent is going to give the red precipitates. If you write Tollens reagent, you can write silver mirror test, but ethane dioic acid, again no reaction or no change you can write. So here comes the last sub question C, that is when propanoic acid is treated with the chlorine gas in presence of ultraviolet rays, a mixture of product is formed. One of these products is 2,2-dichloropropanoic acid. Explain why 2,2-dichloropropanoic acid is stronger than the propanoic acid. Refer to the structure of each compounds in your answer. Now in the propanoic acid, we know that there are 2 chlorine atoms. Now 2 chlorine atoms are electron withdrawing groups. So let's understand that the 2 chlorine atoms, in 2,2-dichloropropanoic acid, is electron withdrawing, or you can even say electron negative. I'm writing here electron withdrawing, which then stabilizes the intermediate carboxylate ion. We can directly write carboxylate or it's an anion. So the OH bond is weaker, breaks easily, and so it is a stronger acid. That is, we are talking about the 2,2-dichloropropanoic acid is stronger because of the 2 electron withdrawing chlorine atoms, which stabilizes the intermediate carboxylate ion. Now let me explain you this. This is the intermediate carboxylate ion, which is stabilized by the electron withdrawing chlorine atoms bonded to this carboxylate ions. Now because of this, the COO minus is stable, not highly electron negative, and that's why it's not going to bond with H plus again once it is donated. So OH bond is weaker, so it's a stronger acid. So here we end with question 10 also. I hope all the explanation is clear. You can refer to earlier 2 videos for the earlier questions.